Professor Andrei Vesnin is an expert in knot theory, spatial graphs, and dimensional topology. Today, he will speak on invariants of spatial graphs and the corresponding nodes and links. Please welcome.
Yeah, thank you very much for the possibility to give a talk at this beautiful conference. I really enjoyed the conference and I understand that everybody tired on the second week. So I prepared a lot of pictures, so I hope you enjoy. So my area is a really low-dimensional topology, but section is called algebraic topology and geometric topology, but all of them are mixed, so I will use something from algebraic topology and maybe present some results which are related to geometric topology. So what I'm going to talk is the following. It's something about special graph. So graphs embedded to the three-dimensional space. And this is situation when we have combinatoric from graphs and topology from the embeddings. So I would like to discuss what kind of relation between them we can find. And after that, I'm going to recall you something about invariance of nodes and links, in particular about the construction of a Jones polynomial, since I'm going to tell you about more general invariant which can be used for special graphs, call it Yamada polynomial. And after that, I would like to present you results about a relation between Yamada polynomial of special graphs and Jones polynomials of nodes and links, which can kind of ingredients of our graph. So generally, the problem, if you know partial information, how to obtain the general information about the structure. And finally, I would like to demonstrate how these graphs are related to hyperbolic free manifolds. I discussed a little bit about geometric topology. So let's start with the definition of our main object. So we can see the graph, usually with finite number of vertices and edges. And we can see the graph which admit loops and multiply edges. And we can see the embedding. So we can consider three-dimensional sphere or Euclidean three-dimensional space. It doesn't matter for our theory. So we can see the embedding, and we can see the image, which we call a special graph. So in particular, you can see the picture like here, and you can meet a lot of such examples in biology and chemistry. Just here a picture of some protein with very nice property, but I'm not to discuss it in details. And this is another example of just formal object which has four vertices and 6 edges, this kind of embedding. And you can see, if you can see the cycle in your graph, so cycle will be embedded to the space as a node. If you have couple of cycles which are disjoint, so this couple will be embedded in the space as a two-component link, and so on. So you see that the theory of special graphs can be considered as a natural extension of the theory of nodes and links, and we consider everything up to some equivalence. And you say that two special graphs are equivalent if there is ambient isotopy of the ambient space, in our case, three-dimensional sphere, which transforms one to another one. So it's very typical situation for nodes and link theory, but now we consider just a little bit more general objects. And of course, we consider everything up to pairwise linear topology, just avoid some wild nodes and wild structures. Okay, so this is our object. And I would like to observe some facts which relate to combinatorics and topology. So the first observation is the following: even our graph is very simple combinatorically, its embedding can be very complicated topologically. There is another example which call it theta graph. So you just take two vertices connected by 3 edges, and theta, because it's a look at the Greek letter theta. You have the two vertices related by 3 edges, and you can consider embedding. When you consider embedding of such a graph in the space, you can see that there are 3 cycles. They are formed by pairs of edges, for example, N1 and 2 given cycles, and 3 given cycles, and 1 and 3 given cycles. So you have 3 cycles. And consider embedding to the space, you'll get 3 nodes. These 3 nodes, K1, K2, K3, just images of cycles. And let us call these nodes constituent nodes of our embedded graphs. Okay, this is just parts of our graph. And there is very interesting result due to Kate Walcott. Oops. Sorry. Oops. Sorry. Maybe I can use cable. It's okay? Okay, now I'm here. Oh. Who's the computer? Okay, okay. Okay, so the results are the following. So for any 3 given nodes, K1, K2, and K3, there exists such embedding of our theta graph in the space that these 3 nodes will be realized by cycles. So in this sense, a very simple graph can be embedded very complicated. And moreover, these 3 nodes, they do not determine special theta graph uniquely. So there are known examples when 3 nodes are trivial, but embedding is not trivial, for example. So you have some balance between combinatorics and topology. This first observation. There are some examples of theta graph. Of course, you can tabulate them similar to the nodes. So people did it. So this is the very initial list. We have 2 vertices connected by 3 edges. And these 14 examples due to Simon, and recently Mariucci tabulated prime special theta graphs having diagrams with at most 7 crossings. So we have vertices and also crossings. The number of such graphs is about 19. Okay? And another observation is the following. If a graph is large combinatorically, then it always have nodes or links. Okay, so if there are a lot of edges, so you can expect something noted or something linked. And maybe the most nice example is complete graph. So you take n vertices, and any 2 are connected by an edge. This just complete graph with an edges. And also you can consider complete bipartite graph when you have n vertices and m vertices, and each from one set connected with each other. So there are very big graphs, and some of them are well known. For example, K4 and K3 are well known non-planar Korotowski graphs. But the Korotowski property related to embedding to the surface, but we consider embedding to the space. It is a bit different. Okay, and about this complete graph, there is a beautiful result due to John Conway and Cameron Gordon, and it was repeatedly shown by Zaks. And there are 2-part results. If you consider the graph with 6, complete graph with 6 vertices, so any embedding of this graph contains 2-component link, non-trivial component link. And similar result if you have 7 vertices and you consider the complete graph with 7 vertices. So any embedding contains a cycle which gives you non-trivial node. So complete graphs embedded very non-trivial topologically. And also there is results obtained by Shimabara for, sorry, let me go back. Okay, here I am. So if you consider bipartite case, so Shimabara proves similar result. If you consider bipartite K44, so any embedding contains 2-component link, and also if you consider embedding of K55, so any embedding contains a non-trivial node. So it's an observation about the completeness of embeddings. And there are some examples. Okay, there are some example. So if you consider the graph K4, so have 4 vertices and 6 edges, so you can find there are 7 cycles in this graph. And each this cycle give you a node in the space. And the result obtained by Yamamoto is the following. So for any 7 graphs, you can consider embedding, which such that this graph, these nodes will be realized as a cycle. So again, embedding can be very complicated. Okay, and if you ask about bigger graphs, for example, K5 and K6, in the same paper of 90, Yamamoto observed that K5 and K6 can be embedded in such a way that all cycles are trivial, give trivial nodes. And the same he observed that it is unknown where similar theorem is true for K5 or K6. Because in this case, you get much more cycles, so more nodes, so you just don't know. And these are some examples. So you have K4, you have 4 vertices connected by 6 edges, and it can be embedded to the space in different way. Just a simple situation where number of crossings is small. Of course, you can consider more complicated. Already, I have another picture on the screen here. Okay, now the same. Okay, so you can ask about the cycles in the graph which are known as Hamiltonian cycle. Hamiltonian cycle, cycle which pass over all vertices. And again, you can ask about knotting or linking property of such big cycles. So the result of Foisy and his students, if you take a Kn starting from 7, there are always knotted Hamiltonian cycles. And also with my students, Anna Letinto, we defined what means Hamiltonian pi of cycles. It means that if you consider 2 cycles which cover all vertices on the graph, so again, you can consider embedding as a space, and you are sure that any embedding will contain linking Hamiltonian pair of cycles. And this direction, there was some generalization done by Mershut and Nikuni. So you can fix P and Q, and you can see the cycles of rank pi and of the rank Q, and again consider embedding. So again, they prove that you can find such kind of linked Hamiltonian pair of cycles. And there are some examples. It's just some diagram of some embedding. And even in this embedding, you can find 2 cycles which give a linked node. I mean, not real node, presented by black and red. Okay, so this situation when there's some balance between combinatorics and topology, and even combinatorics is simple, topology can be very complicated. And if combinatorics is complicated, usually topology is also complicated. And let me recall something about invariance. And I can see the diagram. So my approach will be via Rademeister theorem. And I just recall the classical result obtained by Carl Rademeister in 27. So we are interested in nodes and links in the space, and we consider up to ambient isotopy. And Rademeister reduces this equation to 2-dimensional situation. So we can see the diagrams. So just consider projections of the nodes. We will indicate which is over, which is under. And he proves the theorem that two nodes or links in the space are ambient isotopic if and only if. You can start from any diagram of one node and can derive by finite number of moves to diagram to another one. And moves are just of this 3 type. So these moves called Rademeister moves. They're just local transformation of the diagram. And so you can use such a moves, but generally you don't know what is the sequence of these moves. So there just existence theorem, but it doesn't give you any algorithm how to realize it. Okay, and since we have such a theorem, we can construct invariants of nodes starting from their diagrams, and such idea is due to Kaufman and other people. So let's consider diagram, which is a very local picture. So you have crossing, and you have 4 regions. 2 of them are called, I don't have, okay. call it A and call it B, and you can see the split of your diagram, just a very local transformation when you remove crossings and you remain just splits of type A and B. So if you apply such kind of local transformation in all crossings, you obtain something on the plane. You call it state, similar to state in statistical mechanics. And each element of this state will just closed curve, collection of closed curve on the plane. And we start with such procedure. And for any state, you just take A as number of A splittings and B as number of B splittings, which you use it to arrive to this state. And I want to remark that such kind of coloring was suggested by John Benedict Listing in his first book on topology, which was published in the middle of 19th century. He uses this coloring, but he arrived to the wrong polynomial. But the idea was in his paper, in his book, really. One chapter was devoted to knot theory. Okay, so what we do, we just consider sum, the sum of all possible states. So there are totally two independent states, and we consider something like that in some expression in free variables. And I give you examples. So if you have diagram of the node with such coloring, so one possible state is presented here. So you just use one split A and two splits B. You obtain such collection of curves, which is one possible state. And taking the sum, we obtain such expression like here. And what we want to do after that, we want to obtain something invariant. So to understand, to get expression invariant under randomized removes, we suppose B equal A inverse and D equal this expression in A. And we'll get a polynomial, which call it bracket polynomial, and very often call it Kaufman bracket polynomial. It's not invariant on the first randomized remove, so we need to correct it a little bit. So you can see the right number of a diagram, define it like here. And finally, we arrive to the following result. Due to Louis Kaufman, he defined polynomial in variable variable A, like here. So there is bracket polynomial and multiplier depending on rights and some normalization. And he proves this invariant under randomized move, so invariant under ambient isotopy. And this is just a combinatorial approach to the very famous invariant introduced by Vaughan Jones. So if you change variables, you arrive to Jones polynomial, which is one of the most known in theory of nodes. Okay, and now if you want to go to the special graphs, you have a little bit different situation. We have vertices. So we need to care about the moves where vertices are involved. It's not me. Okay, so we have four, five, and six randomizer moves, some kind of additional moves, okay, thank you. Where vertices are involved, like here, you can cross your arc over the vertex or under the vertex. Also, you can use full twist like here, or you can just use a local twist like here. So a theorem which was proved independently by Louis Kaufman and Seika Yamada in the same year. Two special graphs are isotopic if and only if you can start from any diagram of first one and arrive to any diagram of the second one using this collection of moves. So again, we have diagrammic approach. So we can try to construct invariants, and Yamada did it. So he suggested to consider three types of splits. So if you have a crossing, so you can consider as he denoted as plus split, you do like this one. This is a minus split. And the third one, more interesting, you just create a new vertex. So before it was some graph, it's a finite collection of vertices, but now you create a new one. So your state can have more vertices than original graph. So after applying such a splitting, you will get states which are just graphs in the plane, so planar graphs. So we reduce all crossings. And what we do after that is the following. So we arrive to a combinatorial graph, or just graph on the plane. We don't have any embeddings, it's just combinatorial object. So we can define the following. So we can see the omega number of connected components, and the beta just the first Betty number, so number of edges minus number of edges plus number of connected components. And let's define the following polynomial denoted by h. So we take sum of all subsets of the set of edges. We take -1 in degree omega of the new graph. We take original graph and just remove collection of edges, some collection of edges. So we count number of connected components, and another multiply just minus a minus 2 minus a inverse in degree beta number of the new graphs. So again, we take sum of all possible subsets of the sets of edges, and this is for combinatorial or abstract graph. We are not thinking about embedding this step. And just after that, what we do, too much. Okay, so what we have after that? Just some remark about properties of this H. So very often people discuss graphs, they study the behavior of their invariant under moves like this one. So you have H, and firstly you delete this H, or secondly you contract this H. And many polynomials like flow polynomials, Dicramat polynomials, stat polynomials in graph theory describe it in such a way. So for this H graph, you have the property just if you have a graph and you choose some H, you can delete it or contract, you get a sum. And another important property that if you can see this graph is one-dimensional objects. So if your graphs are equivalent as one-dimensional objects, so you get the same polynomial. And after that, what we do, so we can see the diagram, and we arrive to all possible states. Now we have three possibility to resolve our crossing, so we have totally 3 in degree n states. And each state just a graph, and we take a sum. So what we do, we define Yamada polynomial for special graph. So you can see the all possible states, which are 3 in degree n, and you just take information how we arrive to this state. So a in degree m1 minus m2, and h is polynomial just defined for combinatorial graphs. So it's the idea similar to John's polynomial, but of course the realization is a little bit different because the object is more complicated. So this is Yamada polynomial. And why it is good? Because of the following theorem proved by Yamada. So if we have 2 diagrams of special graphs, which are equivalent to the Rademacher moves, so we get polynomials which are the same up to multiplier. And in the first case, statement about first 5 moves, and a second statement about 6 moves, but we restrict degrees of our graph. Any vertex has a degree at most 3. It's because of different situation in the vertex. It can be rigid vertex or non-rigid playable vertex. So we obtain it invariant for special graphs. We call it Yamada invariant. And of course, you can ask about scaling relation. Scaling relation is a relation 1. And since we know behavior under contracting and deleting H, we have a relation 2. And we have normalization. If you have a trivial loop or just trivial node, so you'll get value a plus I inverse. And very important property, the behavior under mirror image. If you consider mirror image of your diagram, so you just inverse variable. It's also similar to John's polynomial. And there are some examples how it looks. So it is phototabulated K4 graphs. So these examples of Yamada polynomials. So they look like this one. Maybe not so simple. Okay. And also, which kind of information we can obtain? Similar to John's polynomial, it is very interesting in invariant of the polynomial is just a span, so difference between maximal degree and minimal degree of a polynomial. And there are two propositions in this direction. One obtained by Matahashi, Oniyama, and Niyama. So we consider special graphs. We know number of vertices, number of edges. We now know number of components, and we know Betti number. So we have a lower bound for double number of double Betti number and triple number of crossings. So it's some philosophy under that. So you can predict complexity of your object. So if you calculate the span of Yamada polynomial, so you'll know sometimes you cannot decrease number of crossings. And similar result, but for a regular case. So if all graph has degree R, we call it a regular. So we obtain the result is jointly with Andrei Vesnin. So also there are some bounds. So the span of Yamada polynomial bounded by number of vertices, number of crossings, and regularity of vertex. Okay. And of course, these polynomials, so we can start to study the set of zeros. And we did it together with Mohan Central Lay and Selent Lee a few years ago. So we proved that a set of zeros of Yamada polynomials of all special graphs is dense on the complex plane. So it's not isolated set, it's quite general. And also some another invariant was introduced by Yoshinaga. He used it universal algebra related to SL to C. So he constructed such kind of invariant, but he observed it is almost the same as Yamada polynomial. So it is difficult to obtain something new in this direction. Even this kind of quantum invariant is also the same as Yamada. And the proof is based on comparing scalar relations. Okay, so now I'm going to discuss one specific family, and let us consider some modification of Yamada polynomial. So it was polynomial introduced by Jaget. He introduced some Laurent polynomial, which is a special graph, and it can be constructed from a diagram. I'm not going to construct it, and I just use another result to define it. The result was proved by her in the last year. So if you have planar graph, and you have V vertices and E edges, then there is a relation between the Jaget polynomial and Yamada polynomial. You just change variable, you go to a degree 4, and you just subdivide some expression which depend of combinatorics. So I'm interested in study embeddings of K4. So let me think about definition of this Jaget polynomial in such a way. So you can see the modification of Yamada. And I would like to define some links corresponding to embedding of K4. So we start with graph K4 and we embed it to the space. So we have 4 vertices, which are presented here as red points, and we have edges which are presented as a black. And now, so of course, these dots means it's linked it or not in the space. You just don't know part of the picture. Okay, so let's consider the surface, which constructed from our embedding the following way. So we consider edge like some bands, and we consider the surface, which topology just a free functional disk and embedded to the space. So you think about ribbon graphs or band graphs, or just consider such construction. And if you have such a surface in the space, we can ask about boundary of this surface. The boundary of such a surface will be a link embedded to the space, and it will have 4 components. Okay, so starting from our graph, you can see the surface, and we can see the link, which is the boundary of a surface. And if we have a surface, we can consider linking form. So in our case, it will be Seifert form. So what we do, we consider the surface, and we consider 2 curves, closed curves, which belong to this surface, and we just push one of them out to the surface, and we get 2 curves in the space which are linked some way. So we have a linking form between these 2 closed curves. And we take homology groups and we take curves which give us bases on these homology groups. So we define a homology group such a form which corresponds to a linking number between the corresponding curves. So you can define it. It's called a Seifert form. And this situation is typical in knot theory. And embedding of graphs was considered by Kaufman, Simon, Wolkowitz, and Shaw many years ago. And they observed that if you start from a non-planar graph, so you cannot get a surface with zero Seifert form in this situation. So we will restrict ourselves only with planar graph. And in the case of planar graph, they prove the following results. Suppose we have G combinatorial connected prevalent planar graph with in edges. And suppose it's there a plane embedding which is prime with a very natural sense, so this is not connected sums of more simple objects. So there are two possibilities which they observed. If you have at most 6 edges, then for each embedding of our graphs, there is a unique surface with zero Seifert form. So for this surface, our graph is just a spine, but you have some freedom to rotate bands. So there are just unique, and you have more than 6 edges. So there exists embedding with zero Seifert form, or there exists embedding with non-zero Seifert form. And in the case of zero, it is unique. So we build this restriction up to 6 edges. It is natural to consider not a big examples. Example of theta graphs and K4 graphs belong to this class, because in the first case we have just 4 edges, and second just 6 edges. So they satisfy the case 1, and so we can construct some surface which is zero Seifert form, which give us invariant of our special graph. And the case of theta graph was realized in last year by Hyo, and we consider a embedding of K4, which is the maximal possible situation. So what we do, we start with some surface, and we can calculate a linking between edges, and after that we can calculate linking between curves which correspond to linking form, and we can easily find necessary half widths. So you have 6 edges, so you need to apply 6 half widths, which can be found if you know linking between generating edges. So you can find such 6 parameters in Y and 6, and we apply the following. So we have a bent surface, and we apply NY and 2 and 3, so half widths in these places around corresponding edges. So -2 means you do 2 half widths in negative direction, and plus means the positive direction. So after applying such half widths, you obtain a surface which has a zero Seifert form. So this surface is invariant, and the ambient isotopy is invariant of the graph. So we obtain this link, and this is half width is necessary, and we call it associated link. So this is invariant of our special graph. And as I observed before, if you know constituents nodes, so they don't determine K4, embedding of K4. And the problem is to understand how special K graphs are determined by their associated link, or more exactly when they are determined. There is a result obtained by Zhao about theta graphs. So he proved that in some cases the answer is positive, but not all cases are known, even for theta graphs. So we posed the question to understand if we can express Yamada polynomial or special graphs in terms of these ingredients, or these some nodes, or it's qualities or associated nodes. So can we find something on the level of invariance? This is what I'm going to present. So what we do, so we start with embedding of K4 into the space, and we already discussed it, twisting parameters N1 and 6. And now we just normalize the Yamada polynomial. We take minus A4, and we take these degrees, which correspond to twisting. And we proved that if you make such a normalization, you still get an invariant of special graphs. So we work with this normalization of K4, and we will show that this normalized Yamada polynomial can be expressed via normalized Yamada polynomial for subgraphs of our special graphs. And the result is the following. So what we have? We have K4, and then embed K4 to the space. So as we discussed it, we have 7 constituent nodes, which correspond to cycles. And tomorrow we have subgraphs, which are theta subgraphs. So if we just remove one edge, you'll get graph with 2 vertices and 3 edges, which connect these vertices. So our sub-objects are subnodes and subgraphs. And again, the question, what is the relation between the invariants of these objects? And we were lucky to find this relation. This is jointly with my student Olga Shmarin. It was published just months ago in Mathematical Sbornik in a Russian journal. So the result is the following. So let us consider G, the graphic G, be the embedding of K4 in a three-dimensional space. And we consider the following objects. So L, calligraphic L, is just component link associated with our diagram. So this is a link which is a boundary of the surface with zero Seifert form. So we use some twists to construct surface and so to construct this link. Next, we have 6 special graphs which are embedding of the theta subgraph of our original graph. So we can calculate a Yamada polynomial for them. And next, we have cycles in our graph. So we have 7 nodes which correspond to embedding of these cycles in our space. And finally, the result is as following. So normalized Yamada polynomial of special graph G can be calculated as a Jones polynomial of L. L is a 4-component link, and the sum of normalized Yamada polynomial for theta graphs and cycle graphs. Phi just such expression a square plus a minus 2. So we obtained a relation which admits us to calculate invariant of the special graphs via its subgraph, which are nodes and over theta graphs. And so the proof is very boring, I mean, a lot of computations. I don't want to present them here. Okay, and we can continue these expressions. So what we can do, we can consider just links and nodes. So again, what we have here, we start from embedding of K4 in this three-dimensional space. And again, we have L, which is 4-component link associated to a diagram. So again, it means that you can see the surface, which has a zero Seifert form, and you can see this boundary. After that, you do similar for theta subgraphs. So again, you can see the surfaces corresponding to theta subgraphs. You can see the zero Seifert form surfaces, and Li is boundary of corresponding forms. And Kj2 is 2-component links, which are the cabling of consistent nodes of our graph. And now what we have on the left, you have normalized Yamada polynomial for the graph, and on the right you have just Jones polynomials. So the Jones polynomial 4-component link, some of Jones polynomial of 3-component links, and some of Jones polynomial of 2-component links. So we reduce the problem to the following case. So we know partial information about nodes and links, and we can reconstruct invariant of the graph from this information. It's for graphs which are embeddings of complete graph on 3 vertices. And I want to illustrate this example just to make it more clear. So let us consider the graph, which looks like here. So you have two vertices and four edges. It was omega 7 in our table. So we can calculate a normalized Yamada polynomial. It looks like this one. And if you follow our approach, so we can calculate these parameters n1 and 6, and only two of them will be non-trivial, and 1 is minus 2 and 4 is 2. They correspond to age with number 1 and age number 2 is number 4. So we need to use this twist to obtain a link. So the band link will be like this one. We just consider boundary of such a surface, and we apply additional links, minus 2 and plus 2. This, and it will give us 4-component link, and we can calculate John's polynomial for this 4-component link. It looks like here. And by the way, we can observe that this link is hyperbolic, in the sense that the complement of this link is hyperbolic for dimensional manifolds. So we can find a geometrical invariant of it, for example, volume. And for this particular example, the volume is presented here. So this is an invariant of a special graph. And now we go from algebraic topology to geometric topology. So we can use geometric structures. And what about another ingredients? So for theta subgraphs, we have just three possibility. So theta graph theta 1 like here, theta graph theta 2 like here, and all other are just very simple theta graph. So again, we can calculate polynomials. They're like here. And finally, we consider nodes. So you have 7 nodes. Only one of them is non-trivial. It's the figure 8 node, other trivial. So we know how looks normalized Yamada polynomial in these cases. And finally, we arrive to this relation, which due to theorem, of course, just illustration. Okay, yeah. And now I would like to tell something about another construction. So why we are interested in such kind of invariant? It is not only because of application to the proteins and chemistry, but also because of application in theory of three-dimensional manifolds. And such kind of special graphs very natural appear if you consider automorphism of three-dimensional manifolds. So following Bruno Zimmermann, let me give the following definition. So we consider closed, orientable, three-dimensional manifolds. And we say that manifold M is maximally symmetric if there are two conditions. First condition, it admits a Hilbert splitting of genus J. It's not necessarily the minimal one, so it's just some genus J splitting. And it has a finite group of orientation preserved homeomorphism of the manifold, which has a maximal possible order 12 G-1. So it means the maximal possible order in the sense that the handle body live invariant under this group action. So in the case handle bodies is a maximal possible order 12 G-1. So we suppose that if it realizes, in this case, we say that three-dimensional manifold is maximally symmetric in respect to Hilbert decomposition. And the result proved by Bruno Zimmermann in 1985. So he characterized maximally symmetric free manifolds in terms of branch coverings. So what you have, you consider orbifold, containing O sigma Mn. So this orbifold, whereas the underlying space is three-dimensional sphere, and singular set is just such a graph presented in the picture. So you have four vertices marked by black, and you have sigma, just a free string braid, and MAN, some singularity orders which can be 2, 3, 4, or 5, depending on genus. So this is exactly embedding of K4 in space. So it's related to our discussions about different embedding. And one of the most famous example is the smallest three-dimensional manifold. So people try, it is known from the Thurston-Jurgensen theorem about hyperbolic free manifold, then there exists a minimal one. And for many years, people calculated by computer what is a minimal one, and it was found independently by Jeffrey Weeks and by Anatoliy Ivанович Matveyev и Sergei Fomenko и Sergei Ivanovich Matveyev, they found by computer search and the manifold with volume 0, 94, 27, and so on. It's just approximation. So for many years it was just smallest known, and in 2011, Gabay, Meyergov, and Mili proved that there are no smaller manifolds. So they're indeed the smallest one. So this manifold is studied by many people, and particularly it is known it's of genus 2. So it means Higgs decomposition of genus 2, and also it is known there are atom Higgs group of order 12, and we observed with my course Sasha Mednik that these manifolds can be presented in such a form. So it's maximal symmetric, it's Higgs genus 2, and isometry group of this hyperbolic manifold of order 12, and corresponding singular set is the following theta graph, K4 graph, sorry. So you have free-string break, which is presented here. So in standard notation of break group, it is sigma 2 in degree 3, sigma 1 at most, and sigma 2, and corresponding singularity, just for on one H you have singularity 3, and all other H you just have singularity 2. So if you want to study maximal symmetric free manifolds, also studying of embedding of K4 is very useful in this context. So maybe I stop here. So thank you very much.
Okay, thank you, Professor. Any questions or comments?
Thank you for a very nice lecture. I'm curious whether there is an analog of Kuratowski's theorem, an interesting analog of Kuratowski's theorem for planar graphs, for spatial graphs.
So in the case of Kuratowski's theorem, you consider embedding of your graph on the plane.
Yes. And there is a characterization in terms of subgraphs that may or may not exist.
Yes.
And I'm just
exactly K3 and K5. Yes.
Right.
Yeah.
And for spatial graphs, you might ask, like, is an analog? Is there, maybe one needs to consider. So I'm just curious if such a thing is already known, or if there's a conjecture, or like.
I tried to present some results. So if your graph is big enough, so there are always nodes on links. But for some cases, we just don't know.
Okay, so there's no conjecture or even of.
Yeah, for example, if you consider a graph, which is complete graph with 4 vertices, which I discussed. If you have such a graph, so there are 7 cycles, and they can be arbitrary. So maybe all of them are trivial cycles, trivial nodes. Or maybe all of them are the same as you want. So there's a lot of freedom.
Okay, thank you.
Yeah, thank you.
More questions or comments?
So in the last part of your talk, so the polynomials of graphs you talked about before,
Yeah.
Do they give a 3 manifold invariant for corresponding obtained from your last part?
You can do a few things. So what I discussed, you consider 3 manifolds which is branched of this singular set. So you can take invariant from branching set. This for closed case. Another approach, you can consider 3 manifolds with a boundary. And of course, your boundary just some 2-dimensional surfaces, but they can be embedded to the space in a very noticed way. So it is a professor from Australia, Damien Hert, who calculated these graphs as the cusps of 3 manifolds. So here you can provide volumes, a big collection of volumes. And another thing, which I don't present here, we consider the associated nodes and links and we checked all tabulated theta graphs, and we were surprised all links were hyperbolic. And we just used Snappy to check these volumes, and we classified all of them. So you can consider in different contexts.
The second question. So for Jones polynomial, we have colored Jones polynomial. Do you have the colored versions of graph invariants?
For such kind of graph, there is an invariant which was introduced by Francisco Constantino. François Constantino and Robert van der Ween. They defined something similar to Rife-Vero. So it's not exactly to Rife-Vero, but the idea is the same. So you can see the colorings and you can see the same sums. And for this case, they proposed some volume conjecture for special graphs. And this volume conjecture, as well as I know, is proved in the case your graph is just skeleton of polyhedra. In the polyhedral case, it was proved by Giovanni Belletti 3 years ago in Transactions of American Society. And you have a limit of Rife-Vero invariance on the left, and on the right you have volumes of some hyperbolic polyhedra which are right-angled and ideal. So this is kind of colored version.
More questions? Since this last talk,
There are one more question.
Do people study fundamental groups of complements of spatial graphs?
Sure.
Is there something like Vertinger representation for them?
Yeah, sure, it's exactly the same. So if you consider the node, so what you have, you just have a crossings. So in each crossing you have relations similar to Vertinger. And if you have a vertex, so what you have? You have vertex and edge coming out. So you take meridians corresponding to edges. And if you go around the vertex, you just trivial relation. I mean, the product of this generator that give you. So it's a natural generation of the node.
I see. Thank you.
we still have time.
Yeah, okay, maybe just comment. By the way, theta graph was used by some people around Hoey to understand what kind of generalized triangle groups are finite. So there are very famous triangle groups. We have Gokster groups by reflections. But you can generalize, you consider not just the product, but arbitrary word. They call generalized triangle groups. And they studied problem when these groups are finite or infinite. And in some cases, you can reduce to orbifolds. And you get automatically the spherical structure on the orbifold in your finite triangle group. So people did. Yeah.
Okay. So, so your main it is possible to generalize your theorem 2 to K file.
No. You need to use another way because we are based on the result of Kaufman, Walcott, and Simon. That if you consider the surface of Seifert from 0, it is invariant. So you can apply in the case K4 only for some particular invariants when we have 0 Seifert from. Unfortunately. You need to count number of edges. How many edges? Yeah, it seems yes. It seems yes. Maybe yes.
More questions? If there's no questions, let's thank our speaker again.
Thank you.